All right, so last video introduced or hopefully reviewed the concept of relation and function. We also discussed the related notions of equivalence relation, equivalence class, and the notion that we can partition sets using these equivalence classes. Um, so if you're unsure about some of this stuff, I highly suggest reviewing that video. Today, I want to look at an important type of relation um, and how we can use this to talk about modular arithmetic, which is a way to study the integers by kind of collapsing them um, into this finite number of subsets of the integers with special properties. So that's really the goal today. And I think this will probably be the last prerequisite video. So let's get started just with the definition. This will be definition 16, and it's the definition of the congruence relation. So let x and y be integers and fix some integer that is non-zero, call it m. So if x and y differ by a multiple of m, what do we say? We say that x is congruent to y modulo m. And we sometimes will denote this um, in a really fancy looking way. Um, Usually we'll just write like this. So when this concept was introduced, it people thought it deserved this fancy notation, but I think people are a little less concerned with that now. So, and one way to think about this concept of congruence is with a clock. Um, so, you know, if you have an analog clock, you have like these numbers around it, um, like so. And when you count up on this analog clock by the hour, 1, 2, etc., 10, 11, 12, but what happens after 12? Well, we don't go to 13, we go back to 1. Um, so in some sense, 13 equals 1 mod 12. And that is to say, and we can actually show this. So to show that 13 equals 1 mod 12, we need to show that x and y, or 13 and 1, differ by a multiple of 12. Well, of course. So 13 minus 1 is 12. And certainly 12 is a multiple of 12. Since maybe we feel silly writing this, but 12 equals 1 times 12. Um, okay, and then more generally, we would say 14 equals 2 mod 12, a similar argument. 23 equals 11 mod 12. But what happens when we get to 24? Well, so first off, 24 does equal 12 mod 12. That's easy to see. But also, 24 equals 0 mod 12. And indeed, 12 equals 0 mod 12. This shouldn't be too hard to see. Um, so for instance, 24 equals 2 times 24 minus 0. So we're good there. So this is kind of like our archetypal or exemplary example of modular arithmetic. So we might cheekily refer to this as clock math. All right. And that's a good example to keep in mind. Of course, 12, we call this number m the modulus. Um, and of course, here we've used 12 as our modulus, but we could pick any other number just as well, as long as it's a non-zero integer. For instance, when we think about the minute hand on a clock, we're really doing math mod 60. So 60 would be our modulus. I know that might seem like a really conceptual and intuitive explanation, but let's just do a couple more examples with other moduli. All right, let's see. Does 5 equal 5 mod 6? Yeah, since, for example, 6 divides 5 minus 5, which is just 0. Okay, so that's cool. Let's see another example. What about minus 27 equals 1 mod 4? Yeah, we can do that. So minus 27 minus 1 is negative 28. And 4 divides negative 28, right? Since negative 28 equals 4 times minus 7. So that should be pretty clear. All right, so we've introduced this relation called congruence on the integers. And I guess, like, we've introduced this relation, looked at some examples. There are a couple of questions we can ask. Probably the best question is it an equivalence relation? An equivalence relation. And yes, it is. I'm not going to keep you in suspense. So let's formulate and prove this fact. For every fixed non-zero integer m, congruence modulo m is an equivalence relation. And maybe it's a good time, if you are a little forgetful like me, to go back and check the definition of equivalence relation. So pause for a second if you need to do that. That's always a good idea. And now, welcome back. So we need to check 3 things. Reflexivity, symmetry, and transitivity. All right, so reflexivity, number 1. How do we check this? Well, let's let x be an integer. Um, and we want to show that x is congruent to itself mod m. But this isn't hard, right? Because x minus x is 0. So, of course, um, m divides 0. So we win. Okay, number 2 is the symmetry. And suppose x and y are integers, and that x equals y mod m. So we want to show that y equals x mod m. Well, so if x equals y mod m, well, that means that m divides x minus y. And what this really means is that there is some k in the integers such that mk equals x minus y. I don't know why I put that in parentheses, but that's fine. Oh my gosh. Wow, okay. I'm probably going to have to edit that out. So mk equals x minus y. But what does this mean? Well, multiply both sides by -1, and we get that this is y minus x. So indeed, what we've shown is that m divides y minus x, giving symmetry. Finally, let's talk about transitivity. So, and let's say x equals y mod m, and y equals z mod m for some integers x, y, and z. Well, so m divides x minus y, and m divides y minus z. So what this shows is that m divides x minus y plus y minus z. If you're not 100% sure about this, I would check that for yourself. But this is just x minus z, or x minus z. So m divides x minus z, which is exactly what it means for x to equal z mod m. So we've proven that this relation of congruence, mod m, is symmetric, transitive, and reflexive. Not in that order, though. So we're dealing with an equivalence relation here. Let's think a little more. What else is there to talk about? So yeah, we've shown that this is an equivalence relation. So now let's introduce a related definition. So let's fix some modulus m. And remember, this is just a non-zero integer. The integer is mod m. Let's denote it like this. is the set of equivalence classes, or the set of congruence classes, as we call them. We call them congruence classes for this relation. Of the integers modulo m. Under the equivalence relation, congruence modulo m. And I think it's helpful to note that, so if A is one of these congruence classes, a representative of A is just an ordinary integer. So it's some ordinary integer x whose equivalence class is A. So this should be clear. And sometimes, if we're being really informal, we might just drop the bar and write x instead of x bar. But that's really informal, and we would only do that if there's no risk of confusion. So maybe we can do a quick example. And yeah, let's do this. So, and maybe pause and give this a shot yourself if you are curious. Let's determine the equivalence classes, or the congruence classes, of the integers mod 2. So what do we know about equivalence classes that could help us here? We know that congruence classes, being equivalence classes, have to partition the integers. So every integer belongs to exactly one congruence class. So maybe we can use that to somehow limit the computation we need to do. A good first step here, let's just naively try and determine the congruence class of some element and see where we go from there. So maybe it's natural to try to find the congruence class of 0. Well, so for a number to be congruent to 0 mod 2, it means that 2 needs to divide y minus 0. If and only if 2 divides y minus 0. But that just means that 2 divides y. And there's another way to say that. We just mean that y is an even integer. Cool. So what we've got is that 0, the congruence class of 0 more precisely, is just the set of even integers. So that's, I mean, in some sense, half of the integers already taken care of, so that's pretty good. Now let's pick something that doesn't belong to this one and find its equivalence class. What about 1? Well, so we can do a similar thing. So y is congruent to 1 mod m if and only if 2 divides y minus 1. But there's another way to say that, of course. Y is odd. Okay, but every integer is even or odd, right? So we're doing pretty well here, actually. Um, so what we've actually shown is that the integers mod 2 actually just contains these two elements, 0 and 1. Um, and remember, 0 is really the set of even integers, and 1 is the set of odd integers. Um, so we've actually collapsed the integers into two sets. So not bad. Um, maybe as another example, or as an exercise, I'll leave this as an exercise. Determine what this set looks like. Determine the integers mod 3. It shouldn't be too hard. And what we'll find, maybe pause that if you don't want to be spoiled, but what you end up finding is that the integers mod 3 consists of three classes, 0, 1, and 2, with 0 equals 0, or, well, -6, -3, 0, 3, 6, etc. Well, we have 1, 4, 7, -2, -5, etc. And then 2, -4, -1, 2, 5, etc. So you see, in each case, we're just counting by 3. And in general, maybe we can make this observation. For a fixed modulus m, the integers mod m can be described like this. So in particular, there are m elements. And you should be able to convince yourself why this is true. But now let's think about like why might congruences be nice. So part of the term equivalence relation it kind of suggests that maybe this relation should behave like equality. In some sense of the word. So I know that's like a pretty hefty disclaimer, but one way that we can really think about this is through the lens of this lemma here. Namely, that congruent plays nice with respect to a lot of familiar things like addition and multiplication. So let's fix a modulus m in the non-zero integers. If x equals x prime mod m and y equals y prime mod m, then the following ones hold. So x plus y equals x prime plus y prime mod m, and x times y equals x prime times y prime mod m. Okay? So basically what this lemma is telling us we can do is that we can freely compute in terms of representatives of the congruence classes, and we are good to go. So let's prove this. It's not too hard. So say x equals x prime mod m and y equals y prime mod m. Well, then these mean that there exist integers k and l such that mk equals x minus x prime, or actually I think we want to do it like this, equals x prime minus x. We can do this with symmetry. And then ml equals y prime minus y. And those who know LaTeX, this is like a backslash ELL in LaTeX. Don't be confused. So now, let's compute x prime plus y prime. Well, from the relations we have, from the inequalities we established above, x prime is just x plus mk, and y prime is y plus ml. And now it's just a matter of rearrange the parentheses, x plus y plus m times k plus l. And what this actually shows is that x plus y equals x prime plus y prime mod m. You can do a similar trick for multiplication. It's not too hard. It's a little more computational, but I'm sure you can manage. If you've gotten this far. And maybe we should talk about a couple more properties of congruence, just really quickly to keep this video short. So from this lemma, you can actually show that congruence inherits a lot of other properties from just regular arithmetic. Let's list a few of them. One is distributive property. And that is that x times y plus z, we can distribute multiplication over addition in the modulus. We also have stuff like associativity. And this is just that we can rearrange parentheses in this equality. And I think it's also important to note that the identity elements carry over. So 1 times x equals x times 1 equals x mod m. And 0 plus x equals x plus 0 equals x mod m. And of course we also have commutativity. I'm not going to bother writing that one out. And I'm going to list one more thing that is pretty useful. So this isn't really a definition, it's just a useful thing. Well, it is a definition, but I'm not going to list it as such since we kind of mean it informally. So by a multiplicative inverse to a number, we just mean another number. X to the minus 1 is how we denote it, with x times x to the minus 1 equals 1. So in the integers, if we restrict our view to the integers, the only integers with a multiplicative inverse are themselves. Or, sorry, are 0 or minus 1 and 1. They're plus or minus 1. So for instance, minus 1 times minus 1 is 1, and 1 times 1 is 1. no other integers have multiplicative inverses in the set of integers. So what we do, we expand our view to this set. So for other integers to have multiplicative inverses, we go to the rational numbers. And for now, we can kind of think of this as the set of all these fractions, m over n, where the top, or the numerator, is an integer, and the denominator is just a natural number. So we haven't really been formal about that. We will treat this more formally, though. But one thing we might want to think about is what would it mean for an integer to have a multiplicative inverse mod m? So let's fix some modulus. A multiplicative inverse mod m is, for an integer a, is another integer, b, let's call it, such that ab equals 1 mod m. And let's think about this. So first off, I want to make clear that we're not guaranteeing that such a b exists. So mod m, maybe not every integer is invertible under multiplication. But let's give a quick example. So 2 has a multiplicative inverse of 3, mod 5. And why is that? Since 2 times 3 equals 6, which is just 1 mod 5, of course, since 1 and 6 belong to the same congruence class. And I'm just going to state this as a fact that we'll use later. You could actually prove this without too much difficulty. Fix some modulus m. Then an integer has a multiplicative inverse mod m under multiplication mod m if and only if a and m are coprime, or their GCD is 1. So this will be pretty useful, but I think that's pretty much everything for this video. So thank you.